When workers at a mine in Alberta, Canada, sank their excavators into a sandstone bank in March 2011, they had no idea they were about to uncover one of the most puzzling fossils in history. Beneath compact layers of marine sediments appeared an unassuming lump as hard as cement. At first it seemed like just a large mineralized rock, but as part of its surface was cleaned, something no one expected emerged. The unmistakable texture of an animal's armor, complete, intact, almost undeformed, despite the 110 million years since its death. Thus began the story of Borrelopelta markmicheli, the best-preserved nodosaur ever found. The discovery was an anomaly in every sense. Nodosaurids were armored, herbivorous dinosaurs, cousins of ankylosaurs that lived during the early Cretaceous. Their low, wide bodies were covered with osteoderms, bony shields, and long defensive spines. But nothing prepared paleontologists to find one as if it had died just days earlier. The fossil preserved not only its original three-dimensional shape, but also the complete arrangement of its dermal plates. Even pigments were preserved, allowing the reconstruction of reddish and light camouflage patterns on its back, something virtually impossible in most dinosaur remains. The creature was not flattened, as happens with almost all fossils. Its body remained voluminous, muscles hardened by mineralization, and osteoderms in their natural positions. The level of detail was so high that researchers could trace the outline of each scale with their fingers. It was a specimen that seemed to have defied the entropy of time, as if death had caught it in a frozen moment. A major question arose immediately. How did such a heavy terrestrial dinosaur weighing about 1,300 kilograms end up at the bottom of an ancient inland sea? The most likely explanation was surprising. Borrelopelta likely died near the coast, perhaps carried away by a swollen river or a sudden current. Its corpse, swollen by decomposition gases, floated out to sea until it finally sank. Upon reaching the seafloor, the creature landed on its belly, arranging its armor almost as in life. Fine sediments slowly covered it, acting as a protective wrap that prevented crushing. The result was a level of preservation bordering on the impossible. Researchers at the Royal Tyrrell Museum spent over 7,000 hours preparing the fossil. Mark Mitchell, in whose honor the species was named, spent 6 years removing rock grain by grain, a task requiring surgical precision. Each step revealed new surfaces of the armor, large lateral plates, hexagonal scales on the back, and long defensive spines protruding like spears. The dinosaur not only retained its overall structure, it was literally whole. Chemical analysis provided another unexpected twist. Fossilized skin contained remnants of melanin, allowing scientists to deduce the animal's original color. Studies indicated a counter-shading pattern, dark tones on the back and lighter colors on the flanks and belly. This type of camouflage is usually found in animals that need to hide from predators, suggesting that Borrelopelta, despite its formidable armor, was still prey for even larger creatures. Perhaps the fearsome Acrocanthosaurus, one of the dominant predators of its time. The preservation of Borrelopelta also offered a unique window into its internal biology. Inside its stomach, identifiable remains of its last meal were found. Fragments of ferns, leaves, and stems were exceptionally preserved, allowing its diet to be reconstructed with an unprecedented level of accuracy for herbivorous dinosaurs. Small stones, called gastroliths, used to grind food in the digestive tract, similar to modern birds, were also found. Altogether, the fossil revealed aspects of the life, death, and ecology of a dinosaur that could previously only be inferred from partial comparisons. It was a direct testament to the early Cretaceous, preserved as if frozen in a petrified moment. Today, the reconstruction of Borrelopelta is displayed at the Royal Tyrrell Museum, where it has become one of the most famous specimens in the world. Thousands of visitors are amazed when they see its complete armor, so real and detailed that it seems the dinosaur could awaken at any moment. The mosquito in amber, the smallest time capsule of the Cretaceous. When an insect becomes trapped in the sticky sap of a tree, its fate rarely becomes a window into the deep past. Normally, its body decomposes before the resin can harden and capture it forever. However, in a handful of exceptional cases, nature manages to seal an entire moment of prehistory: wings, antennae, legs, and sometimes even traces of its last meal. Of all these microscopic time capsules, none has captured the popular imagination like the mosquito preserved in amber. a tiny fossil offering the chance to observe with precision what an insect from tens of millions of years ago looked like. Interest in these specimens surged with popular culture, but their scientific value is older and far deeper. A mosquito trapped in amber is not just a curiosity, it is a direct testimony of the ecosystem that surrounded it. The resin that encapsulated it came from trees that grew in ancient tropical forests, and over time that resin hardened, fossilized, and turned into amber. Within these solidified droplets, life remained suspended as if time itself had stopped. One of the most important discoveries of a preserved mosquito occurred in the 1980s, when an exceptionally well-preserved specimen was found in late Cretaceous amber deposits, with an estimated age of 46 to 79 million years. What distinguished it from other insect fossils was not only its impeccable condition, but also the presence of microstructures in its abdomen, remnants of partially preserved blood. Although they did not contain intact DNA, which is impossible due to natural molecular degradation, they did show that the mosquito had ingested blood shortly before being trapped. This was irrefutable evidence of its blood-feeding behavior. Scientists had known for decades that many fossil insects reflected modern behaviors, but seeing a Cretaceous mosquito mummified mid-digestion offered a level of detail almost eerie. Its compound eyes preserved the faceted pattern, its antennae, the articulated segments, and its wings showed veins so clear they could be compared to those of living species. The preservation was so precise that evolutionary relationships within culicids, the group that includes modern mosquitoes, could be traced. But the value of amber is not limited to the insect itself. Many pieces also preserve microscopic fragments of plants, fungi, pollen, and even air bubbles trapped at the exact moment the resin began to harden. Paleoclimatologists can analyze the chemical composition of these inclusions to reconstruct the ancient atmosphere, estimating environmental humidity and the composition of the forest where the mosquito was trapped. These reconstructions revealed that Cretaceous ecosystems were rich in plant diversity and dominated by resin-producing conifers, possibly responsible for the preservation of millions of tiny organisms. A fundamental question was what conditions were required to achieve such perfect preservation. The key was the speed of the process. A mosquito can only become trapped if it lands on fresh, still viscous resin. Contact is almost always accidental. One leg sticks, then another, and in a desperate attempt to free itself, it sinks further. The resin covers its body, seals its segments, and envelops its external organs before it can escape. Over time, the resin hardens, becomes buried under sediments, and undergoes chemical transformations that turn it into amber. It is an extraordinary natural process requiring a rare combination of factors: a resinous forest, an insect in exactly the right place, and the absence of disturbances that would destroy the drop before fossilization. Inclusions in amber also allow the study of ecological interactions. Mosquitoes with pollen on their legs have been found, showing that these insects fed not only on blood but also on nectar like their modern descendants. This information is crucial for understanding how insects contributed to the pollination of the first flowering plants, a fundamental process in the biodiversity explosion of the Cretaceous. Other amber fossils have revealed complete predation scenes: a spider catching a fly, two ants fighting each other, or an insect being attacked in mid-air. Although the mosquito in amber does not contain usable DNA, it preserves an intact visual history. Its discovery reminds us that small organisms can teach as much as large dinosaurs because they record everyday aspects of the ecosystem that giant bones cannot show. Today, some of the most famous fossil mosquitoes are in scientific collections across the United States, Europe, and Asia. Their study continues to provide data on the evolution of insect-borne diseases, the diversification of culicids, and the development of resinous forests in the Cretaceous. These fossils have helped trace the origins of certain modern groups and how they interacted with their environments. Archaeopteryx, the bridge between two worlds. When the first Archaeopteryx specimen appeared in 1861 in the Solnhofen quarries of Germany, the scientific world faced a creature that seemed to defy any known classification. It was too reptilian to be a bird and too bird-like to be a reptile. At the height of the evolutionary theory, this fossil became crucial evidence showing for the first time a tangible link between dinosaurs and modern birds. The Solnhofen limestone is renowned for its ability to preserve organisms with extraordinary detail. Its ultra-fine layers recorded even the most delicate structures, and in that environment, Archaeopteryx emerged with complete impressions of its feathers spread on each side of the body. These feathers, with barbs and rachis identical to modern birds, were the feature that revolutionized 19th-century paleontology. It was the first time true feathers were observed in such an ancient creature, and their presence suggested that flight had begun much earlier than previously imagined. But Archaeopteryx was not simply a primitive bird. Its skeleton revealed unmistakably reptilian traits: a long bony tail composed of vertebrae, sharp teeth in its jaws, 3 clawed fingers on each wing, and a skeleton reminiscent of small theropods. Every detail was an evolutionary mosaic linking 2 worlds that seemed incompatible. Scientists studying the first specimen immediately recognized its importance. Charles Darwin, whose Origin of Species had been published just 2 years earlier, saw in Archaeopteryx a powerful confirmation of his theory. Over the years, new specimens appeared, each adding pieces to the evolutionary transition puzzle. To this day, fewer than 20 complete or partial fossils are known, making each one a scientific treasure. The creature's anatomy suggests it was arboreal, or at least capable of maneuvering among branches and perching on them. Its hind legs, with curved claws, indicate it could grip irregular surfaces like many modern birds. However, its flight capability remains debated. Some paleontologists argue it could fly short distances with limited flapping. Others claim it glided from elevated positions. What is certain is that Archaeopteryx combined structures that allowed some form of aerial locomotion, though not as efficient as fully modern birds. A crucial part of its behavior can be inferred from its feathers. The presence of asymmetrical feathers, characteristic of flying birds, is a sign that the animal may have developed minimal active flight capability. Additionally, the discovery of loose feathers in the Solnhofen sedimentary environment suggests these structures were already well developed in various late Jurassic species. The environment where Archaeopteryx lived was fragmented, composed of small tropical islands in a region corresponding to modern southern Germany. The shallow seas surrounding these islands formed enclosed basins ideal for preserving organisms. Sudden death in these areas could result in their fall into anoxic lagoons, where the lack of oxygen prevented decomposition. Thus, each Solnhofen fossil is the product of exceptional circumstances that sealed creatures in limestone layers like delicate prints. The bone structure of Archaeopteryx also provides clues about its locomotion. Although it had hollow bones like birds, they were not as light as those of its modern descendants. Its coracoid, a bone crucial for flight, was relatively small and did not provide the power needed for sustained flapping. Still, its well-proportioned wings, equipped with complete feathers, would have allowed it to escape predators or move between nearby islands. An unexpected insight arose when paleontologists compared the brain of Archaeopteryx with those of modern birds and dinosaurs. Internal scans of the skull revealed it had a relatively large brain for its size, with regions developed for balance and motor coordination. This reinforced the hypothesis of some level of aerial ability, albeit limited. Over the years, new discoveries of feathered dinosaurs in China and other countries confirmed that feathers were not exclusive to Archaeopteryx. In fact, many theropods had partial or complete plumage. However, Archaeopteryx still holds a unique place as the first direct evidence showing evolutionary continuity between dinosaurs and birds. Paleontologists continue to study its specimens using modern techniques such as high-resolution tomography, pigment spectroscopic analysis, and 3D digital reconstructions. These tools have revealed that some of its feathers may have been dark, possibly black or grey, reinforced with melanosomes providing structural strength for flight. The exact color of its plumage remains a mystery, but it is speculated that it combined patterns for camouflage in forested environments. Today, the most complete specimens are housed in museums in Germany, the United States, and the United Kingdom, where they continue to attract the attention of experts and visitors. Diplodocus, the giant that redefined the scale of prehistory. In 1877, at the height of the so-called Bone Wars, a discovery in the arid hills of Morrison, Colorado, would change the world's perception of dinosaur size. That region, covered by late Jurassic sediments, was destined to become one of the most important fossil sites in all of North America. It was there that the first remains of Diplodocus emerged, a sauropod so colossal that paleontologists had to reconsider the limits of animal gigantism. Its discovery marked a before and after in the imagined scale of the remote past. The find occurred in a context of fierce competition. Edward Drinker Cope and Othniel Charles Marsh, the two most influential paleontologists of their time, waged a scientific and personal battle to acquire the most spectacular fossils on the continent. In that atmosphere of urgency and ambition, any bone found in the American West could trigger hurried trips, rushed excavations, and races to publish before the rival. It was one of Marsh's emissaries who discovered the first significant Diplodocus remains. Elongated caudal vertebrae, extraordinarily thin, with bony processes so extended they resembled strips of mineralized wood. The name Diplodocus comes precisely from these double structures that characterize its tail. Over time, more bones appeared, giant dorsal vertebrae, enormous ribs, and later parts of the limbs and neck. Each piece suggested an animal of incredible proportions, longer than any terrestrial vertebrate known at the time. Modern estimates indicate that an adult could exceed 25 meters in length, with some exceptional individuals approaching 30 meters. Diplodocus's form was so unusual that it surprised even the most experienced paleontologists. Its neck was not as thick as other sauropods like Brachiosaurus. Instead, it was long and flexible, formed by delicate vertebrae and joints designed for a wide range of motion. The tail, in contrast, extended like a whip, with over 80 vertebrae gradually tapering to an extremely fine tip. Some studies suggest this whip could have been used as a defensive weapon, capable of producing sonic cracks when moved at high speed. Diplodocus's posture also sparked intense debate. In the late 19th century, dinosaur imagery depicted them as clumsy creatures, almost dragging themselves along. However, Diplodocus's lightweight skeleton, with pneumatic bones, that is, filled with air cavities, suggested it was not a slow animal. Its legs, robust and vertical, resembled the pillars of a modern elephant, capable of supporting its enormous mass without excessive effort. These features prompted a new vision. Sauropods were not apathetic monsters, but active giants with considerable mobility. One of the most revolutionary aspects of the find was the reconstruction of the complete skeleton. In 1907, Andrew Carnegie funded exact copies of Diplodocus to send to museums in Europe and South America. These meticulously assembled exhibits became symbols of prehistoric magnificence. Suddenly, the world could see under one roof the stretched skeleton of a dinosaur the size of a train car. The replica sent to London caused such a sensation that Diplodocus became one of the most recognizable dinosaurs on the planet. The environment in which this colossus lived was a vast river plain, alternating forests, braided rivers, and seasonal lakes. The climate was warm, and the vegetation included tree ferns, conifers, and cycads. Diplodocus likely moved in herds, and its diet consisted of low and mid-growing plants. Its long neck allowed it to sweep large areas without moving the rest of its body, conserving energy. The anatomy of its skull, small compared to its body, and the arrangement of its teeth suggest it stripped leaves but did not chew them. Instead, it relied on a large stomach and possibly gastroliths to process vegetation. The discovery of Diplodocus also provided key insights into sauropod biology. Its bones showed signs of continuous and rapid growth, implying that they reached maturity relatively quickly. This accelerated growth may have been a defensive strategy. The sooner they reached gigantic size, the lower the threat from predators such as Allosaurus, the top hunter of the time. As new specimens were found, Diplodocus anatomy became better defined. Two main species, D. carnegie and D. longus, represent most of the known fossils. However, variation among individuals suggests that real diversity may have been greater. Differences in size, neck proportion, and vertebral shape indicate that these giants had a more complex evolutionary history than originally thought. Dinosaurs in Duel, the fossilized battle that stopped time. In 2006, a discovery in the arid regions of Montana, known as the Badlands, revealed a scene so extraordinary it seemed more like fiction than geological reality. There, buried side by side, emerged the intertwined remains of two dinosaurs that had died in combat, a juvenile ceratopsid, probably a triceratops, and a small tyrannosaurid, identified by some studies as Nanotyrannus, or, according to other interpretations, a juvenile Tyrannosaurus rex. This fossilized pair became immortalized as the dinosaurs in duel, a moment frozen in time capturing the final instant of a fierce fight during the late Cretaceous. The scene was so unusual that it took years for the scientific community to fully accept it. Normally, dinosaur fossils appear disarticulated, scattered by scavengers or time. But in this case, both skeletons were nearly complete and articulated, preserved in direct contact. Their limbs intertwined, tails overlapped, and bite marks, fractures, and wounds suggested a real confrontation. A fight to the death sealed in sediment before the corpses could separate or be disturbed. The sediments that covered them were thin but deposited quickly enough to cover the bodies before weather or scavengers could interfere. This speed, combined with a low-energy environment, perhaps a collapsed dune or sudden sandbank fall, allowed the skeletons to preserve even minute details such as skin impressions and scale patterns. Clear evidence of injuries sustained during the combat was identified on the Tyrannosaurid, including bites on the skull and snout. The ceratopsid exhibited fractures indicating colossal effort in its limbs, possibly from repeated charging attempts to defend itself. The identity of the predator triggered one of the most intense debates in recent paleontology. For decades, some scientists supported the validity of the genus Nanotyrannus, a small, agile tyrannosaurid. Others argued that all fossils assigned to this genus were actually juvenile Tyrannosaurus rex, whose anatomy changed drastically during growth. The exceptionally complete dinosaurs in duel specimen offered an opportunity to resolve this controversy. Detailed studies of its skull, jaw, and joints have provided crucial data, although the debate remains open as more histological comparisons are needed to determine if it is a young animal or a distinct species. Beyond its anatomical value, the fossils preserved evidence of behavior. Bite marks on the ceratopsid and defensive wounds suggest a violent and sudden encounter. The lighter tyrannosaurid, with sharp claws, likely attacked using its agility, while the ceratopsid, though young and smaller than an adult, defended itself with horns and the strength of its forelimbs. The remains show that both animals suffered serious injuries, indicating that neither prevailed completely before sediment collapse trapped them. A deadly fight in which both contenders ended up losing. The discovery, however, was not free from legal and economic controversy. After its discovery, the fossils were involved in a prolonged legal dispute over land ownership and the right to sell them. For nearly a decade, they remained in storage, away from the scientific community, while courts decided their ownership. Finally, in 2020, the specimens were acquired by the North Carolina Museum of Natural Sciences, where they are currently being prepared and studied using state-of-the-art methods. Analytical techniques for this fossil include high-resolution tomography, three-dimensional reconstructions, and microscopic studies of mineralized tissues. These tools allow observation of previously invisible details, such as bone microstructure, joint condition at the time of death, and the exact arrangement of preserved feathers or scales. One of the most important lines of research is the potential to obtain direct information on muscles, tendons, and soft tissues, whose partial preservation has been suggested in several sections of the skeleton. The significance of the dinosaurs in duel goes beyond the spectacle of the scene. It provides insights into predator-prey interactions rarely recorded in the fossil record. Although many fights occurred throughout prehistory, almost none were preserved as they actually happened. Two animals trapped at the exact instant of violence, frozen in a struggle that was never resolved. The simultaneous fossilization of predator and prey provides a direct, physical example of the risks dinosaurs faced in daily life. Today, the skeletons remain under intensive study, and each new observation promises to shed light on their identity, behavior, and the precise cause of their preservation. In the coming years, the mystery of Nanotyrannus may be solved, providing unprecedented data on T-Rex ontogeny. Hadrosaurus, the first giant of America that changed paleontology. In 1858, in a small town in New Jersey called Haddonfield, a chance discovery opened a new chapter in the history of American paleontology. Until that moment, dinosaurs were considered almost mythical creatures, known only from scattered fragments, isolated teeth, and broken bones. But that year, the discovery of Hadrosaurus fulci, a herbivorous ornithischian from the late Cretaceous, represented the first truly complete evidence of a dinosaur in the United States. It was the fossil that transformed American science and the first that allowed for a clear reconstruction of the shape, posture, and proportions of a prehistoric giant. It all began when a local enthusiast, William Parker Falk, heard rumors of giant bones buried on a nearby hill. Intrigued, he organized an excavation, and soon the first pieces emerged. Enormous vertebrae, curved ribs, parts of the pelvis, and limbs. As the work progressed, the skeleton took shape. Although the skull was not fully recovered, the specimen was so large that it surpassed any dinosaur found in America up to that time. This discovery revolutionized the scientific understanding of dinosaurs because for the first time, there was enough material to assemble an almost complete reconstruction. The skeleton was sent to the famous paleontologist Joseph Leidy, who conducted a meticulous analysis. In 1859, Leidy published his conclusions, revealing that it was a large herbivore, capable of both bipedal and quadrupedal locomotion. This posture, which allowed it to use 2 legs for running but 4 for feeding, was novel and puzzling, challenging the traditional view of dinosaurs as clumsy reptiles with limited mobility. Hadrosaurus became the first dinosaur mounted in a museum, unveiled in 1868 at the Academy of Natural Sciences of Philadelphia. Thousands of visitors were amazed by the elevated and dynamic form of the skeleton, unlike any living creature they had ever known. One of the most fascinating aspects of Hadrosaurus was its size. Measuring over 10 meters long and weighing several tons, this herbivore fed on mid-height vegetation. Its long, muscular hind limbs would have allowed it to move quickly to escape predators like Dryptosaurus. The shorter front limbs had hands adapted to hold branches and manipulate plants. Modern analyses suggest it could alternate between quadrupedal walking, ideal for foraging, and bipedal locomotion, more efficient for running, a versatility that probably made it one of the dominant herbivores of its ecosystem. Its hip anatomy was another key point. Unlike reptiles, ornithischian dinosaurs like Hadrosaurus had pelvises adapted to support large body masses, with bones oriented backward for stability. This feature allowed paleontologists to confirm that dinosaurs were a unique group, distinct from modern reptiles. The environment where Hadrosaurus lived was a humid, forested landscape surrounded by slow-flowing rivers and floodplains. In this setting, fast-growing plants like cycads, conifers, and early angiosperms formed the base of its diet. Its teeth, arranged in specialized dental batteries, efficiently ground fibrous vegetation. Although the original skull was not preserved, its close relation to other hadrosaurids indicates it may have had a horny beak useful for cutting shoots and twigs. The discovery also played a fundamental role in popular culture. For much of the American public, Hadrosaurus was their first visual encounter with a realistic dinosaur. Leidy's reconstruction, supported by anatomical evidence and the elevated posture of the skeleton, inspired a new perception of these animals as dynamic creatures. Over time, this fossil became a symbol of American paleontology, and its legacy continues. In 1991, Hadrosaurus folki was declared the official dinosaur of the state of New Jersey. The scientific significance of Hadrosaurus was immense. It opened the door to new expeditions, encouraged museums and universities to systematically study fossil sites across the country, and marked the beginning of professional paleontology in North America. Without it, the large-scale exploration campaigns of the American West might not have occurred with the same intensity, and key figures like Cope and Marsh would not have found the perfect stage for their famous competitions. Despite Hadrosaurus's fame, the available fossil material remains limited. Most of what we know comes from comparisons with other hadrosaurids discovered later. However, this limitation only increases the historical value of the find. Having a relatively complete skeleton in 1858 was such an extraordinary event that it marked a turning point in how prehistoric life was understood. The hobbits of Flores, or Homo floresiensis, the human that should not have existed. In 2003, inside a remote cave on the island of Flores, Indonesia, a team of archaeologists was excavating without great expectations when the light of a flashlight revealed something unexpected. A tiny skull, perfectly preserved and profoundly different from any other known hominin. Its discovery would spark one of the most heated debates in modern anthropology. This small being, named Homo floresiensis, stood only about 1 meter tall and had a brain the size of a grapefruit. But the most puzzling aspect was not its anatomy, but its age. It lived just 50,000 years ago, when Homo sapiens already roamed the planet. The find occurred in the Liangbua cave, an extensive cavern system where sedimentary layers accumulated like pages of a geological book. There, archaeologists from the Indonesian Archaeological Research Center and the University of New England also uncovered arm, leg, pelvis, and foot bones from the same individual, an adult woman approximately 30 years old. This first specimen became known as LB1, the most complete Homo floresiensis skeleton. Surprisingly, it was neither a child nor an individual affected by pathology. LB1 showed coherent body proportions, long arms, proportionate legs, a small but undistorted skull. Its teeth were robust and well-formed, indicating normal development. Its feet, extraordinarily long relative to its body, gave its gait a peculiar appearance. All this suggested that Homo floresiensis was a distinct human species, adapted to an insular environment for thousands of years. The most accepted explanation for its small size is insular dwarfism, an evolutionary phenomenon affecting isolated populations on islands where resources are scarce and selective pressure favors smaller, more efficient bodies. On Flores, giant species like stegodon, a dwarf elephant, and giant lizards coexisted with these small humans, who developed surprisingly complex stone tools. Artifacts from the Liangbua cave show elaborate craftsmanship with polished edges and techniques similar to those used by Homo erectus and Homo sapiens. However, some anatomical aspects of Homo floresiensis raised radical questions. Its brain, barely 400 cubic centimeters, was comparable to that of an Australopithecus, an African hominin that lived 2 to 3 million years ago. How could such a small brain produce such advanced tools? How could these humans hunt buffalo-sized animals or coexist with predators like the Komodo dragon? The contradiction between brain size and complex behavior baffled the scientific community. Detailed studies of the skull revealed that, although small, the brain of Homo floresiensis had a sophisticated internal organization. Regions associated with motor planning and coordination were well developed, likely compensating for its reduced volume. Some researchers propose that Homo floresiensis evolved from Homo erectus, which reached the islands over 1 million years ago and gradually reduced in size. Others suggest its lineage may be even older, tracing back to more primitive hominins that left Africa much earlier than previously accepted. Both hypotheses imply a profound revision of the human family tree. Flores Island also offered clues about their daily challenges. Faunal remains found alongside human bones indicate that these small hominins hunted juvenile stegodon and collected shellfish, tubers, and wild fruits. The presence of burned bones suggests the use of fire, although it is unclear whether they controlled it directly or exploited natural fires. What is clear is that they lived in small communities, highly adapted to their insular environment. One of the longest-standing debates after the discovery was whether LB1 could have been a Homo sapiens with microcephaly or another congenital disease. However, exhaustive comparisons with modern skulls affected by various pathologies revealed significant differences. The shape of the jaw, the length of the arm bones, the wrist structure, and the hip morphology were too distinct to attribute to a simple deformity. Moreover, remains of at least 8 other individuals with similar characteristics were found, confirming that this was a stable population and not isolated cases. Dating of the Liangbua strata revealed another astonishing fact. Homo floresiensis survived until remarkably recent times. Some remains are only 50,000 years old, implying they coexisted with modern humans for millennia. This raises troubling questions. Did Homo sapiens arrive on Flores and displace the hobbits? Was there cultural contact? Or did the small hominins disappear due to environmental changes, habitat erosion, or volcanic eruptions, which are frequent in Indonesia? Local legends on the island speak of creatures called Ebu Gogo, described as small beings living in forests and stealing food. Some anthropologists suggest these stories could be cultural echoes of real encounters with a distinct human species. Although there is no direct evidence, the idea adds a mythical nuance to the mystery of Homo floresiensis. Today, the remains of LB1 and other individuals are preserved in specialized laboratories in Indonesia, where they continue to undergo genetic, morphological, and functional analysis. Megalosaurus, the first dinosaur that science recognized as such. In 1824, when paleontology did not yet exist as a formal discipline, an English scientist named William Buckland presented to the Geological Society of London the remains of a gigantic creature whose bones had been unearthed in a quarry at Stonesfield, near Oxford. It was not the first large fossil found in Europe, but it was the first that someone dared to identify as belonging to a giant, extinct terrestrial reptile. Thus was born Megalosaurus, the first species officially recognized as a dinosaur, decades before the term Dinosauria was coined by Richard Owen in 1842. The original Megalosaurus remains were fragmentary, a partial jaw with sharp teeth, scattered vertebrae, and some long bones. However, what caught Buckland's attention was the enormous size of these elements. The jaw, even incomplete, displayed curved, serrated teeth perfectly designed to tear flesh. Its shape suggested a large predator, very different from modern reptiles. Buckland described the animal as a giant lizard and estimated it could reach more than 9 meters in length, a remarkable figure for the time. Subsequent studies confirmed that Megalosaurus was one of the first large carnivores of the Middle Jurassic. It belonged to the theropod group, direct ancestors of modern birds and distant relatives of predators like Allosaurus. Its skull, elongated and robust, was equipped with blade-like teeth. Its long, muscular hind limbs made it an efficient runner, capable of chasing fast prey. The shorter forelimbs were powerful, with curved claws probably used to hold the animals it hunted. In the 19th century, reconstructions of Megalosaurus were, in retrospect, as imaginative as they were inaccurate. Since scientists only had fragments and analogies with modern reptiles, early models depicted the creature as a colossal, quadrupedal lizard, almost dragon-like, resting on all 4 limbs. It was not until the late 19th century, with advances in comparative anatomy and the discovery of better preserved theropods, that paleontologists understood Megalosaurus was bipedal. The Stonesfield rocks where Megalosaurus was found date to the Middle Jurassic, about 166 million years ago, a period when much of Europe was an archipelago surrounded by warm, shallow seas. The islands were covered with conifer forests, tree ferns, and cycads. In this environment, Megalosaurus would have been one of the main predators. Its prey could include juvenile sauropods, ornithopods, small reptiles, as well as carrion when available. The impact of Megalosaurus's discovery was enormous. Before it, fossils of giant animals were interpreted as remnants of biblical creatures, dragons, or mere geological curiosities. Buckland, along with contemporaries like Gideon Mantell, discoverer of Iguanodon, and Mary Anning, a pioneer in marine fossil research, transformed that speculative world into a science based on evidence. Megalosaurus became the first solid evidence that the Earth had been inhabited by immense creatures, entirely different from any modern animal, which had disappeared long before human history. As more elements were recovered, paleontologists attempted to reconstruct its complete anatomy. Although we lack an articulated Megalosaurus skeleton, the scattered remains, combined with comparisons with other theropods, allow us to approximate its appearance. It is estimated to have reached 7 to 9 meters in length and weighed around 1 ton. Its hind limbs were strong, its rigid tail acted as a counterbalance, and its body was adapted for active hunting. It was not the largest predator of its time, but certainly one of the most formidable and successful. The historical importance of Megalosaurus is also reflected in its presence in the Victorian exhibitions at Crystal Palace Park, where sculptors, based on early scientific interpretations, created life-size models of the first known dinosaurs. Although we now know these sculptures were anatomically incorrect, they represent a milestone in scientific outreach. The mid-19th century public could, for the first time, contemplate physical recreations of extinct creatures, and Megalosaurus became a symbol of the emerging science of paleontology. In recent decades, interest in Megalosaurus has resurged thanks to new discoveries of megalosaurid theropods in Europe, Africa, and South America. These findings have allowed reconstruction of part of its evolutionary lineage and a better understanding of its ecology. The group to which it belongs, Megalosauridae, includes robust predators with similar adaptations, suggesting that Megalosaurus was one of the first representatives of a successful lineage that dominated much of the Middle Jurassic. Lucy, the ancestress who changed human history. In November 1974, in the Awash River Valley, an arid region of the Afar Depression in Ethiopia, a team of paleoanthropologists led by Donald Johanson made one of the most influential discoveries in the study of human origins. Beneath layers of volcanic sediments partially exposed by wind erosion, they found the remains of a small but remarkably complete hominin. This partial skeleton, preserving around 40% of the body, was named Lucy after the song "Lucy in the Sky with Diamonds" by the Beatles, which played in the camp the night of the discovery. Her scientific name, Australopithecus afarensis, soon became a global reference in understanding human evolution. Lucy stood just over 1 meter tall and weighed around 30 kilograms. Her skull had a volume of only 400 cubic centimeters, comparable to a modern chimpanzee. However, her lower limbs revealed something completely unexpected. She walked upright. The shape of her pelvis, the angle of the femur, and the structure of the lumbar vertebrae clearly showed that Lucy was a habitual biped, thousands of years before the genus Homo appeared. This finding demonstrated that bipedal locomotion preceded a significant increase in brain size, a conclusion that transformed the narrative about how and why early hominins adopted upright posture. The landscape surrounding Lucy 3.2 million years ago was a mix of open woodland, savanna, and seasonal waterways. This ecological mosaic favored mobility between trees and the ground, and bipedalism offered key advantages, freeing the hands to carry food, improving visibility over vegetation, and facilitating long-distance movement under the African sun. Lucy's hands, with slightly curved fingers, also indicate she retained some climbing ability, suggesting a gradual evolutionary transition between arboreal and terrestrial life. Lucy's skeleton also allowed researchers to understand the body proportions of Australopithecines. Her ribcage was conical, similar to that of non-human primates, while her lower limbs were longer than expected. This combination revealed mixed locomotion. Although fully capable of walking upright, Lucy probably still used trees as a nighttime refuge, escaping predators such as leopards, archaic hyenas, or giant raptors. One of the most studied aspects of the discovery is the pelvis. Its short, wide shape, adapted to support body weight in a vertical posture, was one of the strongest indicators of early bipedalism. Equally important was the finding of foot bones and ankle joints, which demonstrated an arched structure and a big toe aligned with the others, essential features for efficient bipedal locomotion. The ability to walk long distances with stability was already present in these early hominins. Lucy's significance increased further when other Australopithecus afarensis remains were discovered nearby, including individuals of different ages and sexes. Among these are the famous fossilized footprints of Letoli in Tanzania, preserved in solidified volcanic ash and dated to 3.6 million years ago. Although these footprints were discovered before Lucy, their interpretation gained new strength with the Ethiopian find. Both pieces of evidence together confirmed that bipedalism was an established adaptation long before the appearance of Homo habilis. Lucy also sparked debate about the diversity of hominin species coexisting in Africa during the Pliocene. While some researchers initially suggested that different fossils of the era could all belong to a single variable species, later studies confirmed that multiple species, such as Australopithecus africanus and Paranthropus, coexisted and occupied distinct ecological niches. Australopithecus afarensis, however, was established as one of the most likely direct ancestors of the genus Homo. One of the most persistent debates surrounding Lucy is the cause of her death. Analysis of her bones, particularly the humerus, suggests fractures that may have resulted from a fall from a great height. Some researchers have proposed that Lucy might have fallen from a tree, hitting the ground and sustaining fatal injuries. Although this hypothesis remains debated, it adds a tragic dimension to the study of the skeleton that transformed our understanding of human evolution. Since her discovery, Lucy's remains have become a global symbol of paleoanthropology. Her skeleton has been reproduced in museums worldwide, and her study continues using modern techniques such as computed tomography, allowing internal examination without damaging the bones. Lucy is without a doubt one of the most important fossils ever discovered, not only for what it reveals about the anatomy of our ancestors, but for what it represents: the point at which a small, modest-brained yet perfectly upright creature began a path that would culminate millions of years later in modern humanity. Tyrannosaurus Sue, the king that returned from the Cretaceous. On August 12, 1990, in the vast arid plains of South Dakota, amateur paleontologist Sue Hendrickson was walking around a rock formation known as the Cheyenne River Indian Reservation when she noticed some bones protruding from an eroded cliff. What she discovered that day would forever change the study of dinosaurs and give rise to the world's most famous fossil. Sue, the most complete, best preserved and scientifically valuable Tyrannosaurus rex ever found. With 90% of the skeleton recovered, this 12-meter-long colossus would become an emblem of modern paleontology. The discovery was not the result of chance, but of a near-perfect set of circumstances. After a breakdown in the excavation team's truck, Hendrickson decided to explore the nearby area while waiting for repairs. That's when she saw 3 caudal vertebrae protruding from the sediment. Those vertebrae led to a monumental find, an almost complete skull, gigantic ribs, limbs, dorsal vertebrae, and one of the best-preserved hips ever found in a T-Rex. Preservation was so exceptional that even the nasal bone maintained its original 3-dimensional shape. Initial excavations revealed that Sue had died near a riverbed, possibly after a long life. Subsequent studies of her bones showed healed fractures, infections, and signs of disease, evidence of a predator that survived multiple injuries throughout its existence. Her bone density and robustness indicated she was an exceptionally strong individual. Histological analyses suggest she was around 28 years old at the time of death, an advanced age for a tyrannosaur. This makes her one of the longest-lived specimens ever recorded of her species. Sue's anatomy provided answers to debates that had been open for decades. Her skull, over 1.5 meters long, is so heavy that it can now only be displayed as a replica. The original, too heavy and delicate, is kept under controlled conditions. Her teeth, thick as bananas, were tools designed not only to cut flesh but also to crush bone. The estimated bite force exceeds 35,000 newtons, enough to crush any bone structure of her prey. One of the most revealing findings was the structure of her arms. Although tiny in proportion to the body, their bones showed robust muscle attachments. This indicates that the arms, far from being useless, had specific functions, possibly related to holding prey or maneuvering when rising from the ground. Additionally, Sue's posture, with a horizontal spine and tail extended as a counterbalance, was key in correcting the deeply rooted 20th century misconception of Tyrannosaurus walking upright like a giant kangaroo. Sue's discovery was also marked by an intense legal and financial battle. After her excavation, a dispute arose over the ownership of the land where she was found. Years of disputes followed between the excavation team, the nominal landowner, the federal government, and the Cheyenne River tribe. Ultimately, the fossil was auctioned in 1997 at Sotheby's, reaching a record $8.36 million, becoming the most expensive dinosaur ever sold. Chicago's Field Museum, with the support of private companies, managed to acquire it and ensure its preservation in scientific hands. Once at the museum, an unprecedented restoration process began. For over 2 years, a team of experts cleaned, consolidated, and mounted each bone. The final skeleton, displayed since 2000, shows Sue in a dynamic posture, slightly leaning forward, as if moving powerfully through a Cretaceous landscape. Her presence commands reverent silence. With over 12 meters in length and nearly 4 meters in height at the hips, visitors immediately understand why Tyrannosaurus rex was one of the most fearsome predators in history. Beyond her spectacular appearance, Sue transformed T-Rex paleobiology. Her degree of completeness allowed precise study of musculature, bone thickness, and locomotion biomechanics. It was confirmed that T-Rex was not a fast runner, but a powerful walker capable of pursuing prey for long periods. Her senses were also studied. Sue's skull reveals large cavities for the olfactory lobes, indicating an exceptional sense of smell, and her forward-facing orbits provided binocular vision and depth perception. The fossil also revealed details about diseases and behaviors. Sue shows signs of osteomyelitis and rib injuries, possibly caused by fights with other tyrannosaurs. These marks suggest that T. rex not only hunted but also fought brutally with members of its own species, perhaps over territory, mates, or food. Paraceratherium lynxiense, the giant that surpassed all land mammals. In 2021, a discovery in the Lynxia Basin in Gansu Province, northwest China, revealed new remains of an almost mythical colossus, Paraceratherium lynxiense, the giant hornless rhinoceros that during the Oligocene dominated the open landscapes of Asia as the largest terrestrial mammal that ever existed. Although fragmentary fossils of this lineage had been known since the early 20th century, the emergence of more complete remains in Lynxia offered a unique opportunity to reconstruct the true size, mobility, and ecology of an animal whose size exceeded even that of today's African elephants. Paraceratherium was not a rhinoceros in the modern sense. It belonged to an extinct group of giant perissodactyls, hornless, with surprisingly long limbs and a tall, flexible neck. Its appearance combined the colossal mass of a rhinoceros with the elevated silhouette of a giraffe. Although different species of this genus have been described over time, the new lynxiense fossils helped refine its proportions. An estimated weight between 15 and 20 tons, shoulders reaching 5 meters in height, and a body length approaching 8 meters. It was, in practice, a giant impossible to ignore in its ecosystem. The Lynxia discovery included an almost complete skull, cervical vertebrae, and limb elements preserved in sediments deposited around 26 million years ago. The skull was particularly revealing, over 1.5 meters long, with a long jaw and teeth designed to shred tough, fibrous leaves. The shape of the cervical vertebrae confirmed that the animal had a flexible, muscular neck, capable of raising its head to the tops of trees to access food beyond the reach of most contemporary herbivores. The Oligocene environment in Asia was a vast and changing landscape, with wooded regions interspersed with emerging grasslands. Unlike the large sauropods that had dominated the land millions of years earlier, Paraceratherium lived in drier, temperate ecosystems. Its enormous size not only allowed it to access abundant food in the heights, but also protected it from predators. No known terrestrial carnivore could confront a healthy adult. Threats, when present, were likely focused on young, sick, or elderly individuals. The long and relatively slender limbs of Paraceratherium have been the subject of scientific debate. How could such a heavy animal support itself on such thin legs? The study of lynxiense bones revealed thick bone walls and reinforced joints that efficiently distributed its weight. Its locomotion, though imposing, must have been surprisingly agile. Some paleontologists suggest that these giants could travel long distances in search of food and water, moving with a steady but constant pace across territories that could span tens of kilometers. The newly described species, Paraceratherium lynxiense, provided crucial clues about the dispersal and evolution of these giants. Fossils suggest that these colossal beasts moved between the Indian subcontinent, Central Asia, and China, taking advantage of ecological corridors created during the rise of the Himalayas and the fragmentation of forest habitats. These movements explain the genus's wide geographic distribution and its ability to adapt to different plant environments. One of the most important contributions of the Lynxia remains was the opportunity to better understand cranial structure. The skull shows large cavities for jaw muscles, indicating a powerful bite, though not specialized for grinding low grasses like modern rhinoceroses. Instead, Paraceratherium was a selective leaf browser capable of reaching high tree branches thanks to its extended neck. Its diet included broadleaf tree leaves, tender shoots, and possibly seasonal fruits. Despite its monumental size, Paraceratherium had no horns. Its defense lay in height, strength, and mass. The absence of horns explains the relatively light structure of the skull, which had to be supported by long cervical vertebrae. However, this lack of offensive weaponry did not imply vulnerability. Predators of its time, such as nimravids and other Oligocene carnivores, would rarely have been able to take down a healthy adult. The study of its dentition also helped determine its age range. Dental wear visible in Lynxiense suggests long lifespans, possibly over 40 years, comparable to those of large modern mammals. Growth rate, according to microscopic lines in the bones, was rapid in youth and slow in adulthood, a typical pattern of large herbivores. Gadosaurus aqualignus, the ichthyosaur that emerged from the depths. In 2022, a scientific announcement captured worldwide attention. The official description of a new genus and species of ichthyosaur, Gadosaurus aquilignus, whose exceptionally complete remains had been found in early Jurassic marine deposits. Although the ichthyosaur fossil record is abundant, discovering a specimen so well preserved, with an articulated skeleton, soft tissue impressions, and extremely fine anatomical details, was an event that happens only once per generation. This discovery provided an unprecedented view of the lifestyle of these marine reptiles that dominated the oceans while dinosaurs ruled the land. The Gadosaurus aquilignus fossil was recovered from a coastal quarry where a warm, shallow tropical sea once extended. In the early Jurassic, about 180 million years ago, that region was part of the vast Tethys Ocean, an ecosystem rich in ichthyosaurs, plesiosaurs, ammonites, and primitive fish. The Gadosaurus carcass, likely sunk after a storm or illness, ended up deposited on an anoxic seabed, where the lack of oxygen prevented scavengers from acting and favored extraordinary preservation. The anatomy of the revealed ichthyosaur was astonishing even by the group's standards. It measured around 6 meters in length, with a torpedo-shaped, streamlined body, a well-defined dorsal fin, and a crescent-shaped vertical tail. These features allowed it to reach high speeds underwater, resembling a modern dolphin more than a terrestrial reptile. Its eyes, enormous relative to the skull, indicated exceptional visual capability, probably adapted both for hunting in deep waters and detecting fast-moving silhouettes near the surface. The Gadosaurus aquilignus skull was filled with fine, pointed teeth, arranged in regular rows suggesting a diet of fish and cephalopods. Its long, narrow jaws were designed to capture fast prey, perhaps through short, precise lunges. One of the most notable traits was the presence of sensory canals in the snout, similar to those of modern sharks, which would have allowed detection of minimal vibrations in the water. Preservation of the fossil allowed examination of rarely visible details, such as skin impressions showing smooth, scaleless skin adapted to reduce water friction. Traces of fossilized pigmentation were also identified, indicating dark coloration on the back and lighter shades on the belly. This countershading pattern, common in modern marine animals, made the ichthyosaur less visible to predators or prey, camouflaging it from above and below. Ichthyosaurs underwent rapid evolution after the late Triassic mass extinction, which left ecological gaps in the oceans. Gadosaurus aquilignus represented one of the most advanced forms of the early Jurassic, an agile and highly specialized predator. Its skeleton shows compact and numerous dorsal vertebrae, adapted to generate powerful undulating movements. Narrow, robust ribs suggested a flexible but pressure-resistant thorax for deep diving. The fins, composed of numerous widened phalangeal bones, formed large surfaces that acted as highly precise rudders. Fossil tissue studies suggest that ichthyosaurs, including Gadosaurus, may have been warm-blooded. This hypothesis, supported by isotopic analyses, could explain how they survived in deep or cold waters while maintaining an active metabolism during hunting. The internal structure of the bones, with dense vascularized channels, pointed to fast and sustained growth, typical of animals with high energy demands. The find also revealed details about ichthyosaur reproduction. Embryonic bone remnants were found inside the fossil, confirming that Gadosaurus was viviparous, like other ichthyosaurs. This feature, extremely unusual among reptiles, suggests a highly advanced marine adaptation in which the animal's entire life occurred in the ocean without needing to return to land to nest. The environment in which Gadosaurus aquilignus lived was dynamic and diverse. The marine sediments where it fossilized also contain remains of ammonites, belemnites, and bony fish. These organisms were part of the complex food web supporting large marine predators. Gadosaurus likely competed with other ichthyosaurs and plesiosaurs for the same resources, adapting to specific niches through differences in speed, hunting depth, or prey size. The basin where this specimen was found had been the focus of multiple paleontological expeditions since the mid-20th century, but it was not until the last decade that excavations intensified with modern methods. The use of laser scanners and photogrammetry allowed digital reconstruction of the skeleton in 3D, providing a detailed view of probable musculature and swimming biomechanics. The perfect articulation of the vertebrae allowed modeling how its body undulated underwater, revealing an efficient, fast, and sustained swimming style. Gadosaurus aquilignues has also been fundamental for understanding early ichthyosaur diversity. Its morphology combines primitive traits, such as certain skull elements, with advanced features like widened fins, suggesting it represented a key lineage in the transition toward the highly specialized ichthyosaurs of the Middle Jurassic. The Ganzhou oviparatosaur, a dinosaur sitting on its eternal nest. In December 2021, a scientific announcement shocked the paleontological world. The discovery in Ganzhou, southern China, of an oviparatosaur fossil in a posture never before seen with such detail. It was a theropod dinosaur sitting directly on its nest, with its winged arms extended and 12 eggs perfectly arranged beneath its body. 3 of those eggs contained incredibly well-preserved embryos. The image resembled a petrified photograph of parental care over 70 million years ago, captured in a moment the sand turned into eternity. Oviraptorosaurs were maniraptoran theropods related to modern birds, medium-sized with short, toothless skulls, well-developed feathers, and arms converted into wings. They have been central to a profound shift in public perception. They went from being considered mere egg thieves to recognized as attentive social animals surprisingly dedicated to raising their young. The Ganzhou discovery not only confirmed this image, but elevated it to an unparalleled level of evidence. The specimen was found in the Nangxiong Formation, a region rich in late Cretaceous dinosaur fossils. Sediments indicate the area was a warm, humid river basin with occasional rapid flooding events. It was likely one of these sudden events that caused the animal's death while incubating its nest. The rapid sediment flow covered it before it could escape, sealing its last posture in stone. What distinguishes this fossil from all previous discoveries is the exceptional combination of context, preservation, and direct behavioral evidence. The animal's position is unmistakable, sitting on the nest with arms extended and belly resting over the eggs. This posture exactly matches that of modern birds when incubating. The radial arrangement of the eggs, organized in rings, suggests that the nest was meticulously constructed, probably with plant material or clay soil that did not preserve. The embryos in 3 of the eggs were so complete that their developmental stage could be analyzed. Some were in advanced phases, with vertebrae, limbs, and skull elements well formed. This degree of development suggests that the Oviraptorosaur was actively regulating nest temperature, as embryos require constant heat to reach such late stages. This behavior is a strong indicator of advanced thermoregulation, bringing these dinosaurs even closer to bird-like behavior. The adult's anatomy reinforces all observations. The fossil preserves partial feather impressions on the arms, suggesting the animal warmed the eggs through a combination of direct body contact and wing coverage. Its legs, folded to the sides, were positioned outside the circle of eggs, avoiding crushing them. This posture reflects sophisticated, highly adapted reproductive behavior. Chemical analysis of the eggs revealed multiple shell layers, indicating they were laid in pairs, possibly sequentially. This matches observations in other oviraptorosaurs. Females could have 2 functional oviducts, producing pairs of eggs simultaneously. The nest distribution in concentric rings suggests that the adult may have rotated to arrange them neatly, a strategy that maximizes space and ensures even heat distribution. But the fossil also revealed another surprising clue: the presence of small pebbles in the adult's abdominal region. These gastroliths, stones ingested to help grind food, confirm that the animal was omnivorous. The Oviraptorosaur likely combined a diet of plants, seeds, small vertebrates, and eggs, not necessarily its own but stolen from other dinosaurs and animals. This dietary variety would have been key to its survival in changing environments. Preservation of the hind limbs allowed detailed study of how these animals walked. The Oviraptorosaur's legs were long and agile, with robust toes enabling quick movements through vegetation or over sandy terrain. This suggests the adult could alternate between active life and prolonged nest care, implying a high level of energy and dedication. This fossil not only revealed behavior but also social context. The species, although not fully identified at the time of description, probably lived in small groups and exhibited some degree of parental cooperation. Nests found in other parts of China indicate that some oviraptorosaurs nested in colonies, a strategy common among modern birds to protect eggs from predators. Researchers used micro-CT scanners to analyze the embryos without damaging the eggs. Three-dimensional images revealed that the embryos had developing feathers and well-defined beaks. The orientation of their necks and limbs indicates they were in hatching position, ready to break the shell from within. This suggests the adult's death occurred shortly before birth, making this fossilized scene a critical and unrepeatable moment. Emberosaurus rathi, the first dinosaur of Zimbabwe and a clue to the origin of sauropods. Between 2017 and 2019, in the remote Zambezi Valley, an international team of paleontologists discovered a fossil that would completely change the understanding of the origin and early dispersal of dinosaurs. Emberosaurus rathi, the oldest dinosaur ever found in Zimbabwe and one of the oldest in all of Africa. Its bones, preserved in an astonishing state of integrity, emerged from sedimentary formations dated to approximately 230 million years ago during the late Triassic, a time when dinosaurs were just beginning to walk on Earth. The discovery was part of the Mid-Zambezi Basin project aimed at mapping the prehistoric fauna of the region. As researchers began excavating the pebbly Arcos formation, they found small, delicate vertebrae almost in their original alignment. As excavation progressed, the pelvis, limbs, and cranial elements emerged. What was remarkable was not only the specimen's age, but its extraordinary completeness, with nearly 80% of the skeleton preserved. In a continent where the oldest dinosaurs were known only from fragments, this integrity was unprecedented. Emberosaurus rathi was a small, agile dinosaur, about 1.8 meters long and weighing no more than 30 kilograms. Its anatomy suggests it belonged to early sauropodomorphs, the lineage that millions of years later would give rise to gigantic sauropods like Diplodocus and Brachiosaurus. But Emberosaurus was the opposite of those colossi. Bipedal, with slender legs, a long, balanced tail, a moderately extended neck, and a small skull equipped with teeth adapted for a herbivorous or possibly omnivorous diet. The discovery was particularly important for its biogeographic context. Until then, most of the oldest dinosaurs had been found in South America, in regions like Ixigualasto in Argentina, and to a lesser extent in India. The similarities between Emberosaurus and Triassic South American dinosaurs confirmed a long-debated hypothesis. During the late Triassic, Pangaea was not only united, but had specific climate zones that restricted the dispersal of early dinosaurs. They did not expand randomly. They followed environmental corridors determined by temperature and humidity. The presence of Emberosaurus in Zimbabwe demonstrated that these primitive dinosaurs reached southern Africa almost simultaneously with South America, suggesting a rapid and structured movement eastward across the supercontinent. Its appearance in tropical temperate sediments supports the idea that early dinosaurs preferred relatively humid environments, away from the driest interior zones of Pangaea. Emberosaurus anatomy reveals its place in this evolutionary story. Its pelvis shows primitive features typical of early sauropodomorphs, including a structure that allowed an efficient semi-upright posture. The hind limbs were long relative to the body and ended in feet with 3 functional toes suitable for running. This adaptation suggests an active animal, possibly diurnal, capable of moving quickly to feed or evade late Triassic predators such as Rauisuchians and early carnivorous cynodonts. The skull, though fragmented, showed lanceolate teeth with gently serrated edges, indicative of a diet based on leaves, stems, and soft vegetation. Unlike the large sauropods, which needed to consume massive amounts of plants, Emberosaurus likely had a moderate metabolism and flexible diet. Its small size and lightweight structure allowed it to thrive in an ecosystem where resources could fluctuate seasonally. The associated fauna found alongside Emberosaurus provides a more complete picture of the Zambezi Valley during its life. Among the sediments appeared remains of herbivorous armored reptiles called etosaurs, primitive crocodiliforms, procolophonids, and even cynodonts representing early stages of mammals. These findings indicate a diverse ecosystem with multiple ecological niches that favored evolutionary experimentation prior to the absolute dominance of dinosaurs. What makes Emberosaurus an exceptional fossil is the clarity with which it documents a critical moment, the beginning of the global expansion of dinosaurs. Its age nearly coincides with that of the first South American dinosaurs, reinforcing the idea that there was no single epicenter for the emergence of dinosaurs. but a simultaneous process across similar climate regions of Pangaea. This pattern provides a coherent explanation for the early dispersal of the group and, particularly, for the rise of sauropodomorphs. The study of Mbirosaurus also allowed detailed analysis of its skeleton. The cervical vertebrae indicate it had a relatively mobile neck, useful for browsing low and mid-height vegetation. The hip structure, with a long backward-oriented ilium, represents an intermediate stage between early dinosaurs and more advanced sauropodomorphs. Limb proportions show a transition between bipedal locomotion and occasional emerging quadrupedal use, a trait that millions of years later culminated in the fully quadrupedal anatomy of Jurassic giants. Researchers digitally reconstructed the skeleton using 3D scans, allowing precise understanding of its posture and biomechanics. According to these models, Mbirosaurus could run nimbly and maintain body balance with ease. Its low center of gravity and rigid tail made it a stable runner, which would have been crucial in an ecosystem with large non-dinosaurian archosaur predators. Spicomelus afer, the strangest armored dinosaur of the African Jurassic. In 2021, a scientific study revealed the existence of a dinosaur so peculiar that paleontologists had to completely reconsider the evolution of armored dinosaurs. Its name was Spicomelus afer, and it came from Jurassic sediments in Morocco. Although the discovery consisted of a limited set of bones, especially a rib spectacularly fused with a dermal spine, its uniqueness was extreme enough to identify a new species, a new genus, and, most remarkably, to make it the oldest recorded armored dinosaur. The fossil was discovered in the Tinghir region of the High Atlas, a known Jurassic fossil-rich area. The sediments date to around 168 million years ago during the Middle Jurassic, a period when armored dinosaurs, called thyreophorans, were just beginning to diversify. Until then, paleontologists believed that ankylosaurs and stegosaurs followed separate evolutionary lines, with armor gradually developing over tens of millions of years. Spicomelus challenged this idea unexpectedly. The central element of the fossil was a rib surrounded by a tubular, elongated, bony structure, a pointed spine fused directly to the bone. This combination was unprecedented. No other known dinosaur has an osteoderm, i.e., a dermal plate fully welded to a rib. In all other thyreophorans, plates develop in the skin or are partially integrated but never fully fused to the axial skeleton. This unique feature allowed identification of Spicomelus as an extremely primitive yet surprisingly specialized armored dinosaur. The spine's morphology suggests it served a clear defensive function. It was rigid, sharp, and angled, ideal for deterring lateral predator attacks. Some researchers proposed that Spicomelus may have had multiple similar spines along its sides, forming a protective barrier that made it hard to bite or topple. Although a complete skeleton is lacking, comparisons with other thyreophorans indicate that Spicomelus was probably a medium-sized animal, 2 to 4 meters long. It had a low posture, a robust body, and strong limbs, traits common in ancestors of stegosaurs and ankylosaurs. But its armor was unlike any other. While ankylosaurs developed thick shields and fused plates in symmetrical patterns, and stegosaurs produced tall dorsal plates, Spicomelus showed an independent and early level of innovation, as if evolution had experimented with different forms of protection before settling on the most familiar designs. One of the most intriguing aspects is its age. The Middle Jurassic has historically been a period with scarce thyreophoran fossils, leaving a gap in the evolutionary history of these animals. The presence of Spicomelus in Africa demonstrates that armored dinosaurs were already diversified and geographically widespread much earlier than previously thought. Its distribution also suggests that early thyreophorans may have originated in Gondwana, the southern supercontinent, rather than exclusively in Laurasia, as previously believed. The find also has important implications for understanding Africa's paleogeography during the Jurassic. The presence of such a specialized dinosaur in the Atlas region indicates ecological corridors, allowing terrestrial fauna dispersal between Africa and other land masses. The ecosystems of northern Africa, which now seem arid and inhospitable, were once green, humid, and rich in plant and animal diversity. Histological analysis of the bone revealed a rapid growth pattern and well-vascularized internal structure, suggesting a relatively high metabolism. This aligns with the hypothesis that many Jurassic dinosaurs, even herbivores, had higher metabolic rates than previously thought. The armored spines being fused to the skeleton would have required substantial energy and calcium to form, reinforcing the idea of active growth. Spicomelus also occupies a special place in African paleontology history. For decades, the continent's fossils were underestimated or overlooked compared to the more famous sites of North America, Europe, or Asia. This discovery highlighted Africa's potential as one of the most promising regions for uncovering key species that clarify early phases of dinosaur evolution. The genus name Spicomelus means collar of spines, a direct reference to its most striking feature. The epithet apha, meaning African, honors its geographic origin. Although it is a single specimen, its scientific value is monumental. It represents a completely unexpected basal line within Thyreophorans, a branch that may have gone extinct without leaving direct descendants, but demonstrates that armor evolution in dinosaurs was more complex and diverse than previously imagined.